Hi everybody. We continue with our graphs and we get to using these graphs really for real life problems because graphs are a very they are interesting on their own accord. There's a field in mathematics called graph theory, but the reason it's popular also is because it has a lot of applications to other different sciences and different problems, and that's where we're going to get to. And so remember a weak a simplistic way of saying what a graph is, it's just a bunch of points that are connected by, let's call them roads. Okay, so we have all these things that we can connect, and we have connections there, and sometimes this one, and so something like that. So we call the points or the nodes or vertices, and we call these roads edges. Now, of course, if we the picture, the image of this network of roads suggests one thing, right? That is that we would travel on those roads, okay, and or walk on those roads. And so this is the notion of a path. So a path or a walk. It's the same. Some people use path, some people will walk. Sometimes they mean slightly different things with that, but let's not concern ourselves with that. And what does that mean? It's just going from one point to another point, using, of course, the edges. So, for instance, if I go from A to B, what a path would be, therefore, is you go first this edge, and then this edge. Oh, no, don't do that. No, I don't know why he did that. So this edge, and then this edge. So we have this path consists of three edges. So let's make some names here. E, F, and G. A bit rather random. I assigned these names. So a path will be so from A to C to D to B. So notice that when we are dealing with a simple graph, which is very often the case, but we'll see sometimes we need to talk about more complicated graphs where you have multi-edges and so on. But for a simple graph, there is an edge or there is no edge between certain two vertices, and therefore if I write, what I write here is a list of vertices that are connected by each vertex is followed by adjacent vertex. So A is adjacent to C, C is adjacent to D, D is adjacent to B, and that is what a path is. Okay, if I write this down, a path as a list of vertices, then I mean this is how I have to walk. And it completely gives me, if of course, I cannot write down this, for instance, A, F, B. You say, oh, that's a path from A to B, right? Because from A to F and F to B. No, because there is no edge from A to F, so this is not a valid path. Okay, we could write it down, but it's not a path because there's no edge between A and F. Now, does it mean that's the only way I can get to A to B? No, of course not. There could be many paths. So let's do one in green here. I could go. Some parts of the path are unique because I have to go to C because A is only connected to C. But once I'm in C, I have a little bit of leeway. I can go to F and then I can do this one. So this would therefore be the path A, C, F, B. And you might say, okay, I think this is all, Professor. Well, yes and no, because look, I'm going to do something rather silly. What I can do is, okay, I go from A, sorry, I'll do this in purple. So this is a path from A to C, and then I go to C. Okay, so I'm going from A to C, then I go from D, C to D, and then I said, oh, Chu, I forgot something in C. I have to go back to C, and then I go back to D, or rather you say, oh, I changed my mind, and now I'm going to go this way. Or I could have gone back to D and then go. So each of these are valid paths. So let me write down the path that I have now. Let's perhaps do the same color. The purple path is the path A, C, D, C, F, B. So what you see is that there's no restriction on traveling the same road twice. There's also no restriction on going through the same vertex twice or more. And sometimes you have to. Let's make a different graph here. So here's a different graph, a slightly different one. Again, I'm not making a very sophisticated graph, so I'll just put a bunch of things here. So we have say this way, 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 let's say. And I want to travel from, let's say, A to B again. That's small a and b, like we always been doing. So, what is it that I wanted to do here? Oh, sorry. Okay, let me make a little bit more here. And so here is a, so I have to get some more names, right? A, C, D, let's call this E, F, G, and H. Again, the names do not matter. Once I have designed the names, I can. So consider this path. From A to C to D to A to E to B. That is a path that goes from A to B. It is a valid path. So if I write this down, you have to check that it's a path. Wait, what does it mean is, so is this a path? Well, from A to C, from C to D, from C to D, from D to A, from A to E, and from E to B. Notice that I did not travel the same road twice. That I didn't do, but I visited A twice. You might say, that's silly, why do you do that? Sure. And so we have this notion of, well, that's not, that is often something we cannot avoid. And for instance, here is, we will talk later about it, but for instance, let me get me a simple example here. And I want to go from A, so this is the let's say, the graph. And the goal is, we will talk about this later, we'll give names to this. This is called the Hamilton circuit, we'll discuss it in a couple of sessions. Is I want to go from A and visit each city once. So I want a path that goes A, so this is B, C, D, E, that travels through the graph and goes to every, so let make one more extra here perhaps, or perhaps even an extra here, just to show you that it's, the many, again, there's many solutions. And here's a solution for this. A, B, C, A, D, E. Let's look at, verify that this is indeed the graph. This is the graph. Well, from A to B, from B to C, from C to A. Well, let me get rid of this guy here. We're not using it. From A to D and from D to E. My point is that if I want to travel through all of the cities, then I will have to go through A at least once, because at least twice, because somehow there is the things to the left of A and the things to the right of A, and I can only reach them by going through A. So you see, repeating a vertex is something that is very often impossible to avoid. However, what we do want to avoid is to use the same edge. That kind of sounds silly, right? The thing that I did here, going to C and then go back, then you should have done that, basically, right? That's kind of an empty move. So a path that doesn't have a double vertex, is a path in which not vertex, a path in, let me write it down, a path with no double edge. So with no edge is used twice, with no double edge. No, that's perhaps. Okay, let me rephrase this. A path in which no edge is traversed. We say also traversed, walk to, traversed twice, is called simple. These are the simple paths. And the other ones, in the sense that, okay, if you traverse an edge twice, then that's no longer simple. Now, it doesn't necessarily, traversing an edge twice does not necessarily mean that this is what you need to do, that this is the kind of thing you do. You could have a path like this, for instance. So let's take one more example here. So let's suppose we have this. So here is I'm going to just draw it, right? So here I would go this way, that way, that way, this way, that way. Yeah, that's not what I want to do. That way, and come back this way and that way. This is a path that I now wrote. You saw what happened. I traveled this edge twice, but what I did is I traveled on each of the edges. That's another question. Is that possible to do that? Or what is the best way to travel all the edges? So, right? Now it's, so sometimes it's where we are interested in the edges, sometimes we're interested in the vertices. So let's give a little bit of examples where these paths and so come in. What is a path? We have seen so-called acquaintance graphs. So where there's a path, so we have a bunch of people, and there's a path between one person and another person if they know each other. Okay, so so the acquaintance graph that was discussed, I think, in 10.1 already. Acquaintance. So there's an edge between person A and person B. This means they know each other. And of course, I mean, everybody knows quite a sort of people. Generally, we know about 1,000 people, or perhaps more even, that we are acquainted with. No, it's they know each other, right? Acquainted means it's not that, of course, I know the President of the United States, but he doesn't know me. So that's not an acquaintance, right? It has to be both directions. But for instance, you and every one of you, we know each other. Although unfortunately we have never met in person, that doesn't mean that we don't know each other, right? Knowing each other, meaning I know your name, you know my name, I know some things about you. Unfortunately, I also know you're great, and you know some things about me. You hear me talk all the time, so we are acquainted. Now, for instance, take your friend. You have or your sister. Your younger sister, who is not in college yet. So there's absolutely no reason that I would be acquainted with her, right? So this is me, and this is you. So each of you can imagine that you are the second one here, and this is your little sister. I don't know whether you have one like that, but okay, let's imagine that you have that. So there is no edge between me and your little sister, but there is a path between them, right? Because via you, I'm not acquainted to your little sister, but I'm acquainted via you, who is acquainted. So we talk about, if there's a path from one to the other, we can talk about the distance. The distance is the length of the path that connects one vertex with another. Of course, we have seen that there are different paths that, like in this example here on top, we had at least 3 different paths going from A to B. So the distance here depends on what path you take. Or you could say it's the smallest length of a path between them, and this in this case would be 1, 2, 3. But this is also 1, 2, 3 path. And the purple part that I had, 1, 2, 3, 4, 5, is definitely not the closest. So you could say the distance between A and B is 3. That's the smallest path, length of a path between them. If there is at least a path between them, right? So that's the distance of a length of a path. So this graph is kind of... before I say this, perhaps it makes more sense, I give you one more notion here. Let me erase a little bit of these graphs here. Then I have a little bit more space. These were just examples, right? Let's look at this graph here. No, that's not what I want to do. Sorry, I want this one here, this one. Sorry, I should be a little bit... Sorry, let me do this again. I have to be a little bit... Make it a little bit nicer, right, guys? So I have this one, I have this one, this one, this one, this one. I'll make it a little bit curved that they don't hit each other. Okay, so here's the graph. Okay, here is A and here is B. Okay, so what is the distance between A and B, you might say? Okay, so let's find the path between A and B and try to find the smallest part. But this is a problem. If I am at A, well, I can go either this way or I can go that way. But then there's not much choice. So basically, the only path to A is basically like circling around here these three vertices. I can never get to B. So this is an example of this graph. The graph is not connected. So what it means, so this is a negation of a statement. What does it mean to connected? So a connected graph, connected means there is a path between any two vertices. This is a very important concept, this notion of connected. So a graph is connected means that there's a path between any two vertices. So for instance, this original graph is connected, right? Because from any vertex I can go to any other vertex. Some are kind of central here, so it's easy to go from F to C and from F to G. Some of them are a little bit more isolated. You have to go from here, from G to A, you have to go this way, this way, this way, or from G to E, you have to go this way. So you can, there's simple graphs, right? But if the graphs get bigger and bigger, it gets harder and harder to see whether they're connected or not. It's not easy to see that these are connected, right? This was not a connected graph because there's no path from A to B. So this is this example here, so just to make sure that this is an example of a not connected graph, okay? But the other graphs that were here and the ones before that I drew were all connected. So the acquaintance graph, now that's a question, is the acquaintance graph connected? In other words, let's take it a smaller scope. Let's look at all the people that say are okay. I'm going to increase the scope. Let's first think about all the students in CityTech. Do you think that's a connected graph? Yes. Why? Because, okay, two students might not know each other. No. Yeah, I have to be, perhaps that statement, I cannot really prove that, right? Is any two students not connected or not? But it feels like it is, right? Because it feels like, okay, I'm taking this class, and so assuming that you know everybody in class, I know this is different in the virtual setup, but imagine in a regular setup, in the in-person classes, you know the people in your class, presumably, right? At least you interact with them, not perhaps everybody, but a bunch of them. Now, those people have classes with other people. So, sure, there is going to be connections going from one student to another student. It might take a while. Perhaps it's harder to get a path from a freshman to somebody who is there in college already, is fifth year. There's perhaps less connection, but you can imagine that there's a connection. Let me say it a little bit more larger. What about everybody in New York City? Do you think there is a acquaintance graph is possible? Is that connected? If everybody that lives in New York City, you might first think, I don't see if somebody lives in the Bronx and someone in Staten Island, well, how on earth are they gonna be connected to each other? But okay, think a little bit about. Of course, now you're looking for connection points that through which you can connect each other. For instance, the mayor of New York City might be a good vertex to try to find a path. So here is, for instance, okay. Here again is, here is another graph. This is New York City, okay, and here is me, and here is somebody that lives in. I'm gonna just write down an address. 143 West 15, apartment 15A. Assuming that it exists. I just put and this, and I'm taking the youngest person in this household. I have to come up with somebody, right? But of course I cannot say, oh, let's take somebody that everybody knows, because then it gets a little bit too easy, right, to find acquaintance. But this is somebody nobody knows who he is. But okay. He probably knows his parents, right? It might be a little kid, right? So the little kid, let's say it's a 3-year-old kid, for sake of argument. his parents, he knows his parents, right? So that's the first connection. He's connected to his parents. So let's go here. Here is his dad. Okay, so this is a kid. Okay, the kid that lives on 132 West 15th Street in apartment 15A. I don't know that exists. People, don't go look it up. So he's dad. Now the dad probably knows the super of that building. Okay. Now the supers, okay, they belong to an organization, supers. So perhaps they use the union head. The supers are very often members of a union, so the union head. Now, me, I know my super because I also live in a condominium, so I also know my super. I'm saying, okay, it might be that this particular kid lives in an apartment building without super. What do I know? But I'm just saying a possibility, right? I know my super. Oh, and that super is going to know the union head. Look, so I can always find connections through central people with higher status perhaps, because somehow we all eventually link to them, right? The same, for instance, I used here the union head of the union of superintendents, but it could have been also the mayor of New York City, perhaps. I could have gone that way. I'm not going to, my super doesn't know the mayor of, well, he might know, he knows the mayor of New York City, but it's the other way around, that's the problem, right? But my super perhaps knows, he's befriended with an official. His family member is in the city council. Why not, right? And then immediately you have the link to the city, to de Blasio. Okay, so you see. So now what about the whole world? And even there, it is believed that there is actually that most people belong. That is the connected graph. Now, of course, it's kind of a little bit, well, probably it's not, because there are still in deep parts of the Amazon and in New Zealand and so, there are still regions we actually have never yet explored, so there might be even tribes that have never met any of the rest of the world, and of course then we cannot be acquainted with them. That will be a disconnected component. So when I use the connected, so now I can say, okay, if the graph is not connected, I can look at all the points that are connected to a given vertex. And that forms what we call a connected component. So in this example, the connected components, so connected component is therefore all vertices that are connected to a given vertex, right? So here we see that there are two connected components. I do them into colors, and this is the second one. So here we have two connected components. So my example of the whole world, where it is believed that most people have a connection, that there's a path between any two people in the world, I should say, with the caveat that there might be some tribes deep in the Amazon we have not discovered yet, and that therefore completely have never had any contact with the outside world. So they would form this little small connected component, but the huge component that is the rest of the world is assumed to be connected. And again, how do you find these connections? Very often to heads of state, for instance, because that is how you can globally. So if I'm here in the States and I have to connect to somebody, let's say in Botswana, how am I ever going to do this? Well, okay, so my way would be, I'm just giving a part of the route. I don't know the guy in Botswana, so he has to come up with his own connections. But for instance, I can connect to, let's say, my father-in-law was a journalist. It was the head of the Iranian journalism press agency. So he knew the Shah. The Shah of Iran, I don't know whether you know about this, but before Iran was so-called an Islamic Republic, it was a kingdom, a monarchy. So he knows that, he knew the Shah has passed away. Unfortunately, my father-in-law also has passed away, but let's keep that, not just the people that are living currently, but people that have lived also. Let's put all that together on our graph. Why not, right? And of course, so once I'm at the Shah of Iran, it's very easy to get to some other head of state. Of course, the Shah of Iran is not alive anymore, but his son is. Of course, he knew, and his son is clearly known by the President of the United States because he actually is in so-called exile in California, but he's still called the monarch, the monarchical party. He's still the royalists that support him, and they know, and so on. So you can see in about 3 steps, I'm connected already to the President of the United States. I don't know him. I know the President of the United States. As I'm making this video, it's one guy. I hope that by the time you guys watch this video, it's going to be another guy, but we don't know yet. And anyway, so this connection is a path, and so this is the assumption that everybody, and then of course, once I'm connected to the President of the United States, and the guy in Botswana is, for instance, connected eventually to the President of Botswana, then the connection is there. Okay, perhaps with one more interstep, because some presidents, like the current one, is not very well known, popular, and doesn't know much about the rest of the world, so he might not know actually who the President of Botswana is, if he knows where Botswana is. Okay, go on. But let me give another example of this. It's so-called the collaboration graph. So this is the collaboration graph. Collaboration. And I give 2 examples. I'm a mathematician, and in mathematics there's a very well-known collaboration graph. As a mathematician, you either sometimes publish papers on your own, but you often also write papers with friends or colleagues or other people. Okay, and so you can ask about how many collaboration steps are there between me and even a colleague of mine. Like in Graduate Center, I have several colleagues of mine. We meet with seminars, but some of these colleagues I've never written a paper with. Yet there is a connection because I've written a paper with one guy, and that guy has actually written a paper with the second guy, and that guy has written a paper with my colleague. So again, this is assumed to be a connected graph. And in fact, sometimes some people are well known for having a lot of publications written together with other authors. And one of these persons is called Erdos. So he's a Hungarian mathematician. His field was graph theory, so that's appropriately to mention, one of his fields, because he was a polymath almost. He has many papers, and therefore also many collaborators. And so the Erdos graph, and honestly, this is okay. It's a little bit of a game, but it is, people calculate these things, is how many steps are you away from Erdos. And here is an example of look at the. Let me not do this. Let me do it this way. I'll enlarge this. So here is an example. Moving this thing is always so hard. Yeah, the left column you see here, the Erdos number is just the distance in this graph between you and Erdos. So of course, what do you mean distance 0? That means the point itself, the vertex itself, in this case, which is Erdos. And how many people has this? Of course, just one. And this, what is this? Here. What is this then? What does this represent, this number, 504? These are the 504 people. Erdos has passed away, so this number cannot change anymore. Is the number of people that have written a paper with Erdos. Right? If the distance is 1, means that you're actually a neighbor, that you're adjacent. That's distance 1, right? So that's about 500 people. Then the people that have distance 2, meaning there's a path that goes the path from Erdos to them in 2 steps, but no path in 1 step. Okay, it's not a collaborator. There's about 6,500 people. That's quite a lot of. All of a sudden, it blows up, right? And then people in distance 3 away. So that means they have written a paper with somebody who's written a paper with somebody else who's written a paper. Wait, let's see. So here is me, and it is written with my advisor, actually, I think I have a paper, and my advisor with some person, I forget the name now, so some mathematician here, and then this is an Erdos. 1, 2, 3, yeah. Erdos. Erdos is already here. Actually, it might be not my advisor, it might be some other person that have written a colleague. Yeah, it's actually a colleague of, I think, if I look it up, it's a colleague of me. You can look it up. There are places where a colleague of me, doesn't matter who he is at MIT actually. An MIT colleague. This is me, this is a mathematician, I forget who this is, and then this is Erdos. This is the path. I'm in this cluster here, in this cluster, one of the 33,000 people that are distance 3 from Erdos. Because I've written a paper together with my colleague in MIT, and he has written a paper with, I don't know who that is, and that guy has written a paper with Erdos. That's how it works. And this is in the world of mathematics. Now, you see the bulk of it is at distance 4 and 5. I mean, before I wrote this paper with my colleague, I think it was through my advisor, and then the distance was 4. So I used to be in this one, but then since I wrote with this guy, I get into this one. And of course, since the Erdos himself passed away, and therefore his collaborators will get older and probably less and less collaborate with other people. These numbers here, these first numbers are not going to change much anymore, but this will change a lot, of course. There are people that are kind of quite distant, but very, very few people. It says, what does it mean? It means that they're kind of isolated, they do their own job, and they're doing on a topic that is completely different of what Erdos would work on. That's kind of what it means. So a similar graph exists, and that has perhaps more known, because who knows mathematicians, right? But this is movie, and this is about Kevin Bacon. He's an actor, and at some point he says, oh, I know everybody in Hollywood, I ever made a movie with them, or they were in a movie with somebody I was in a movie with. That was his claim. Now, that was a bit exaggerated claim. Well, look at how many. So so there's an edge between two actors if they have in the same movie. If they appear in the same movie. So this is actor A and actor B. If they appear in the same movie, well, it's easy to see, right? It's either you're in the same movie or not. Now, of course, it could be that they're in several movies together, but then we just put one edge. Or we could put multiple edges, it doesn't matter, but let's just put just one edge between them. And so again, here is Kevin Bacon. Kevin Bacon is, I don't know whether you know the actor, but otherwise go look him up. And so, for instance, Kevin Bacon have a movie together with actor A, or actress A, say, and actress A has a movie together with actress B, and so the distance from Kevin Bacon would be 2. So here we have, of course, again, distance 0 is Kevin Bacon himself, distance 1, that would be all, look how many people were in all, but of course, in a movie there are quite a lot of characters, right, a lot of actors, so it's not surprising that this number is rather high, but this is more surprising, distance 2. This is already 100 times more than this number. That's quite surprising, right, that so many people, and distance 3 is almost the majority of all actors and actresses in Hollywood are at least distance 3. His claim, by the way, remember, his claim is distance, this was his claim, right? That everybody in Hollywood is either in a movie with me or has been in a movie with an actor who was with me. That would be these people. Now, that claim was not correct. He should have made one step 3, and then he's kind of has almost 1 million actors or actresses that are connected to him. Okay, and this is very often one can use this as a game. Like, for instance, you give you mention one of your favorite actors or actresses, and then you have to find now a connection to Kevin Bacon. Like, okay, this actor was in this movie, and in that movie was also this guy, and so on. Well, if you're a movie buff, you can do this. And of course, you can do this with other things as well, where we have highly connected graphs, and like that, and with people that are very central that. So here, of course, Kevin Bacon is one example, but there are other actors that you could do this with, or actresses that you could do with. This Meryl Streep, for instance, if you people that are a bit of my age know her better probably than you guys. You can do the same thing. and one assumes that famous actresses or actresses very often have a similar division of graphs. Okay, so that's the talk about paths. Okay, so now a very important type of path is a circuit. A circuit is a path that starts and ends at the same vertex. So again, let's make a little bit of a randomly drawn graph here. So let's say this and that, and I have this and this and that and that and this and this and that. Those guys. Let's connect these guys and these guys. Let's connect it. Okay. So what would be a circuit, for instance, from A would be a walk, a path that I have to be in this color. That goes one there, and then perhaps we go there, and then we want. I'm going to make it a little bit longer. There are shorter ones, but I have to return to A. So here, if we give names to these guys, is this B and C and D. Let me only know the ones that I need here: A, B, C, D, A. So I do write the A in the back to make the connection back to A. So in other words, a path is something where these two guys are the same. A circuit is something where these two guys are okay. And then a simple circuit is a circuit that is also simple as a path. In other words, that where we don't have double edges. Of course, I could have done the A, B, who goes to C, and say, oh, I'll go back and then C and then A, right? That would be going this way. I go to A, C, and go back and this and that. That would not be a simple circuit because I kind of doubled here up, but that was of course silly, and I could have avoided it. Now that's not the only. This is a silly way of doubling a path, but there might be less silly ways. We will see this when we get to more complicated graphs or more special situations. Okay, but just to have an idea of what a circuit is. Okay. Good. There is also the notion of a path in the directed graph, and there it's important that we have an arrow. So if I'm going to not say too much about them because we will use it less, but it's just good to understand. So okay. So here is A, B, C, and D. So this would be a path A, B, D from A to D, right? This is in the indirected graph. Now I'm going to make a directed graph in it and do it in red by putting now arrows here. So A and this and this and this. So now is this a graph in this directed? Is this a path in the directed graph? What is the condition of what is the restriction in the directed graph is I can walk a path only in the direction it has. So in other words, I can go from A to B, but I cannot go from B to A. So this is a valid walk step from A to B, but the next one is not, because the arrow, it goes the other way. So this is not a valid path in this directed graph. There is one, A, C, D. So here A connects to D in this way. Okay. What about B? Can I go from B to A? Is there a walk from B to A? No, because unfortunately B has only incoming arrows and no outgoing, so there's no way to get away from B. So here B is so-called is not connected to the rest of the graph, and so this is the notion of I don't want to say too much about it. So of strongly connected. Yeah, so this is B. B is not part of the strong. This is not a strongly connected graph because there is no directed path from B to A. Okay. Now, very often when we have a directed graph, what we can always do is ignore the directions, and then of course there will be more paths, and then this is a connected graph. So, in other words, let me write this down as an undirected graph. If you think of this as an undirected graph, in other words, ignoring the arrows, then it is connected. As a directed graph, this is not connected. So there's a difference, okay? And for instance, an example of a directed graph is the web graph. So the web graph is there is an arrow from one website to another website if there is a link. If website A has a link to website B, okay? And it's very often there are web pages that somebody who has set up a web page but then doesn't really know what to do with it. He probably has one link to somebody else's web page, but nobody have ever linked to him. That these things happen. There's going to be web pages like that, or web pages that have a very specific goal that everybody might go to, but nobody from that web page. That's it. If you're on that web page, there's no links to click on them there. It's bad design. We know now that there should always be a link to the home page, to a higher level page, but in the early days, one paid, or even nowadays, many people don't pay attention to that. So there are many connected components in the undirected graph. As a directed graph, there are many things that are not connected. However, strangely enough, there is what is called. Let me see here. There's the name. Where did I go? What happened? Oh, sorry, I jumped somehow into the wrong. Give me a sec. It's a name that I want to use here. This is the giant strongly connected component. The giant strongly connected component in the web graph. So there is, what does that mean? These are all the web pages in this giant strongly connected component have links. If you have two web pages in that belong to this collection, then there is always, you can always go from one web page to that other web page by linking to various, clicking on links on web page, and you get to a new web page, you click on the link there and you keep going, and if you do it in a good way, you will get to the other website, and vice versa. So any two websites in this giant strongly connected component are linked together, and it is estimated to be rather big. It is almost 90%, I think, of the web pages belong to this so-called. What was it? Oh, sorry, it's 53 million vertices, but that is of 20 years ago. I'm sure it's an order of magnitude bigger nowadays. So this is an older study of the web, the World Wide Web. That's why I call it World Wide Web, right? So this is amazing that there is this one huge component that connects everything to everything. And if you design your website properly, that's how it should be. There should be something that points to your website. For instance, my homepage, the website that you guys go through, is listed on the department website, and the department website is connected to the CityTech website. The CityTech website is connected to CUNY wide websites. So there are keep links that go from, and when you're on one of my pages, not every page, but many pages allow you to link back to my home, to the home page, to the home, as they call it. I don't know if you tried that out. There's a couple of links on top of my web page, so you can see how this works. Okay, so that's about these. Yes. Directed graphs, but now I want to get a little bit, I want to split this again in two parts. So I want to talk about connectivity a little bit more. So imagine another important area where these graphs are used to model is networks, right? Computer networks. So you have a computer network, and so suppose this is a computer network here. And so let's think about this as routers, and these are connection between the routers. This is a connected network. So in other words, any two computers in that network can communicate with each other. However, there's a little bit of a problem here is, suppose, because these routers can fail, or they can crash, or they can shut down, or whatever, there can be problem with one of them. Look at this one. If this one would fail, in other words, if this collapses, look at what happens with the all the connections. They're all gone. And what happens now, all of a sudden, well, the guy is out. Of course, he's out, so he cannot connect to anybody. But the other four here, these four here, they were perfectly fine, and all of a sudden they cannot connect to each other anymore. That's not some situation that we want to be in. So what this shows is that this was what is called okay. So I'm going to use this is a cut vertex. So this is a cut vertex. What does that mean? That is a vertex that, if removed, the graph becomes disconnected. Not connected. So let me write the word disconnected. That's what one uses for this. So we start from a connected graph. Yeah, I hope that's okay. And then, so this is not part. Let me do this in different color. So this is a cut vertex, that orange guy here. For instance, what is not a cut vertex is this guy. So, okay, so this is a cut vertex, and so here is a non-cut vertex, this guy. If this one fails, let's see what happens. Of course, it itself fails. That's unavoidable, but everything else is still connected. Okay? So this is not a cut vertex, therefore. Not a cut vertex. So cut vertices in this kind of circumstances are kind of delicate points. This is a point, if that fails, the whole network fails. Let's say a network fails if it gets disconnected. So the first thing we want to do is give a network. So let me give you a network here, for instance. I'll give one that is from the book. Just copying it here. So I have to make it a bit bigger, otherwise you have to see the difference between a crossing and an actual vertex, right? So remember, look at this guy. This is a network. So the question is, what are the cut vertices? So remember what is a cut vertex? That if you remove it, you get a disconnected graph. Well, in this case, what we could do is, this is the beauty of my app here, is I can do one at a time. If I remove this, do I get a disconnected graph? No, everything is still connected, so that's dot one. What about this one? Oh, yes, because look, this guy is no longer connected. So this wasn't a cut vertex. So let's mark this one. So this is a cut vertex. Okay. What about the next one here? What do you think? No. Okay. You see the next one? Yes, this is going to be one, because now in the previous case I got really isolated things, but now I get actually two networks still, but the networks themselves are no longer connected. So you might say, okay, these guys can still talk to each other, right? But these guys cannot talk to any of these guys anymore. So it's still considered a cut edge. Okay. So I should mark this here. That's also cut edge. There's one more. Do you see it? It's this one, right? Because now again I get two networks, but the networks themselves are no longer connected. So that's also one, and the other three are not. And so there are several examples. I will do some homework problems like that, and you can play around with it. So that is the cut vertex. Now there's another thing. This is when a router fails. But what also can happen is that the fiber cable that connects these routers, this network, fails. That also can fail. So now we're not talking about cut vertices, but we're talking about cut edges. So, yeah, let me do it. Cut. Sorry, let me go back in black. I want to keep these colors for. So what is a cut edge? Is if removed, graph becomes disconnected. Same thing. Now, perhaps I should have stressed this. When you remove a vertex, obviously you have to remove all the edges that are connected to that vertex because the vertex is no longer there. Now, if you remove an edge, that's a different story, right? If I remove an edge, so let's see where I can remove this edge. There are still a lot of edges. I only remove one edge, whereas if I remove a vertex, a lot of edges are removed. All the edges that are connected to that vertex. So it's a different situation, okay? So was this one that I just erased? So let me do it again here. Is this a cut edge? No, because everything is still connected. So this is not a cut edge. Do you see a cut edge? Cut edge. So let me make this a cut edge in green. So cut edge. Do you see one in this graph? This one, right? Here. If I remove this guy, then I have disconnected the left top guy from the rest of the network. So that is a cut edge. In other words, this is a fiber cable that should not, if this fiber cable fails, then the network fails. There is, I think, one more cut edge. You see it? This one. Right? Because now, if that fails, then these two, the left and the right hand sides, are no longer connected. So that's another example. Oh, no. So should add this. So this was one. This was one. But I think that's the only one, right? Everything else is still connected. So cut edges do exist. And again, it's something that... So what is now the thing? We don't want cut vertices. We don't want cut edges in a network. All right, and that's the notion of vertex, about the notion of vertex cut. Is a set of vertices when removed, graph is disconnected again. So instead of one, we can now have several ones. And the idea is this. Perhaps let's give me an example here. So here's a graph. I do this one here. Yeah, let me just do this one here. Okay, that is clear what the graph is here. Okay, so this one has no cut vertex. You have to check this, but you can see every vertex. If even one of these vertices fail, the others are still connected. Perhaps no longer. If for instance this bottom one fails, now the path from here to there is part of one length 1, 2, 3, 4, whereas the original path was much shorter, was 1, 2. That has changed, but as far as failure, so the network will be a bit slower. Obviously, if something fails, it's gonna. Otherwise, it was not necessary. It was redundant, right? If it fails, it's gonna put stress on the network, but it is not disconnected, so the network doesn't fail. So this has no cut vertex, but it had a vertex cut. Sorry, I really don't like this word, but sorry, where is this? So vertex. A better word, I think, is a vertex cut or a separating set. I like this word better. It says much. cut vertex, a vertex cut, it sounds like almost like a limerick, right? But it's a separating set is a collection of vertices that if all of those fails, then it gets disconnected. And here's an example, right? So I'm claiming these guys, these two guys here, if I remove those, let's do that. Now I get disconnected, okay? So, oh, sorry. So here we have the vertex cut. There's no cut vertex, but there is a vertex cut. There's always a vertex cut, by the way, if you think about it. Just remove almost everything, okay? The vertex cut here would be, let's call this A, B, C, D, E, F, and G. A vertex cut would be B and F. That's not the only one, I think. I think there are other ones. For instance, A and E would also. Let's see. What happens, for instance, if I do A and F? See, quite a lot that they get disconnected. And so we have now the vertex connectivity, sorry, that's the word I was looking for. The vertex connectivity, and that is called kappa of a graph G. So G is a graph, and what is kappa? That is the smallest size of a vertex cut. Or separating set. In other words, it means, let's put it in terms of networks, it makes it much more sense. It is the number of computers that have to fail, the smallest number of computers, no, how to say this? The smallest collection of computers, if those fail, the network fails. Okay? So in this case, this is called, the number is denoted kappa, the Greek letter kappa. So the kappa of this graph G, what is this? Well, it was 2. Let's first think about what does this mean, kappa gamma, if kappa of a graph G is 1. What does it mean? That means that there is a vertex cut of size 1, which is simply a cut vertex. It's a single vertex. So this was an example of a graph where the was 1 because each of these red guys was an example of such a failure of size 1. But there are no failures of size 1 in this one, but there are failures of size 2. Let's say it this way. I hope then it becomes intuitively clear what it means. There are failures of size 2, and that's why this has cut vertex 2. So, sorry, so let me say, so kappa of a graph is 1 means there is a vertex cut. There is a cut vertex. See, now I get myself confused. There is a cut vertex, namely, and that of size 1. There's something of size 1. The kappa of a graph is bigger than 1 means no cut vertex. But of course, as I said, it might be not 1, but 2 make it fail. And you can imagine at some point there's going to be a number of things that fail. So here is an example of something a little bit, let's see here. Yeah, let's look at this here. Can I disconnect this? Well, let's see. If I remove this guy, it's not disconnected. If I remove this guy, it's connected. Okay, so this had cut vertex 2. And then see, this is what it means, right? In 2 steps, I get a disconnected graph. So now, there is a little problem here with this particular graph. Do you know what this graph is? This was K5, the complete graph on 5 vertices. Every 2, all possible edges are there. That's what it means. Every 2 vertices are adjacent. That's a complete graph. Let's see how long it takes to disconnect this graph. So I can remove this. Oh, sorry, this was not, oh, okay, sorry. I see immediately that what I had was not there's a connection missing. What is the connection that I was missing? This was not a, okay, sorry. Perhaps I was actually trying to draw this one. Let's look at this graph now, sorry. Come back to K5 in a sec. This is not K5. Why is it not K5? This one is missing. Okay, let's try to disconnect this. And of course, trying to disconnect, we always go for those with high degrees, because these are the ones, most connections make it fail. So let's remove this guy. Now, after remove this, can I remove one of them so that it gets disconnected? I don't think so, right? If I remove this, it's connected. If I remove this, connected. If I remove this, connected. If I remove this, connected. So removing this right-hand guy that I just did gives me a graph that still it has no vertex cut vertex, sorry. Okay, so we are tempted to think that this might be 3 even, right? I repeat, removing this, that will be, if this would be disconnected, it would be 1. It isn't. If I connect this and it would be disconnected, the connectivity would have been 2. It isn't. So the connectivity is probably going to be 3 here. And of course, I cannot just argue from one example, because I might have tried to cut something simple that made it I might have not chosen the right vertex to eliminate. So let's try another one. Let's try to eliminate this one. But you see the same problem, right? Once I remove this, I still have something that has no cut vertex. So this graph, therefore, has connectivity 3. You have to, 3 of them have to fail before it gets disconnected. And let's do this. What would be the 3B? Okay, 1, 2, 3. Of course, we have removed 3, so there are only 2 left now. That's because there were only 5. But that's okay. Now, what about K5? Oh, so okay, K5. That would be 1 more. This is now a complete graph. Let's try to disconnect this one. Okay, here we disconnect it. Do 1. Okay, that doesn't work. So remember, it's not 1. It's not 2. It's not 3. Well, what to do here? Is it 4 or not? Well, in this special case, we say it is 4. Although technically this is not there's only one connected component. We call this disconnected because it's on its own. So this is a one example exception of the kind of definition. It's a bit tedious. I'm gonna ignore it. For one thing, when we talk about connectivity, we never talk about complete graphs, because obviously complete graphs is the best guarantee against failure of a network if every 2 computers in the network are connected. Of course, that will never fail except when everything fails, right? So let's not talk about complete graphs. So that's the connectivity of a graph. Now, there's also, remember, as there were cut vertices, there are cut edges. So we can ask the same thing. How many edges, how many fiber connections, how many edges in a network, so in the network this corresponds to fiber connections between 2 computers, have to fail before the network fails, meaning there's no connection. Okay? Of course, if there is a cut edge, then that will be 1, because you remove that cut edge and there we are. But if there's no cut edge, and here is an example where there was no cut edge, so this is, and let me write this here, no cut edge in this graph. Simply, you can see almost, right, wherever edge you removed, it's still connected. But there is a cut edge, so now we have an edge cut, which is so an edge cut. So what is an edge cut? An edge cut is so it's the same definition here as there. So an edge cut is a set of edges. When removed, it becomes disconnected. Set of edges once removed graph is disconnected. And then lambda of the graph is the size of the smallest edge cut. So in a network, this is if a network has, say, and this is called it's edge connectivity. This is called the edge connectivity. So if a network has edge connectivity 2, what does it mean? That means that there are two edges, not every two edges, but there are two edges that if both of them fail, the network fails. And so here's an example where this graph here, so we have seen that this graph has vertex connectivity 2. What is its edge connectivity of this graph here? Well, again, there are, if I remove this edge as well as this edge, sorry, this was not supposed to remove this one, then we have disconnected the graph. So we see that also the answer is 2 here. It's not 1 because we know that any single one cannot, if any single one fails, it's okay. But if two of them, not every two, right? Here's an example of two that can fail. Here there are two that fail, but the thing is still connected. So be careful. The same for vertex connectivity as well as edge connectivity. It's the worst case scenario. It doesn't mean that it's the general situation. In general situation, there many more have to fail before the whole thing gets disconnected, right? For instance, just to give an example, in the vertex case. So let me go back here. Suppose, so we know that the vertex connectivity is 2. In other words, there are two vertices. If they fail, the network connects, but not every two are like that. For instance, suppose this one fails, and this one fails. Again, this should have not been erased. Sorry, that is a bit weird. Right, so let me look at it, right? So watch me. This one should remove these two. This one should remove these two. Okay, this time it's better. And this one should remove these. I see. You see what happened here? It removed this by accident, right? So, but it's an example of 3 edges that I remove. Sorry, 3 vertices that I remove and it's still connected. So keep in mind these connectivity numbers, edge connectivity and vertex connectivity, are worst case scenarios. So the worst case scenarios in both cases is 2. And so what we want is networks that are have high connectivity numbers, but of course not too high, like a complete graph, because that would be expensive, right? So you'll find you have to weigh against expensive versus connectivity. The number of connections versus connectivity. And let's see here, just give me, yes. And there is one inequality here. I'm just going to give you the equality and then I'm going to stop. So the edge connectivity, sorry, the vertex connectivity is always smaller or equal to the edge connectivity. Here it was equal. They were both 2. And there are examples, and I will go to the homeworks, and perhaps next time I'll give you other examples where they can be different. But if they are different, this one has to be the biggest. This one has to be the biggest, okay? And they're all less than the minimum degree of all the vertices. So in this case, let's go back. Okay, I have to redraw this guy because it's too long to go back. I don't want to remember. This is how this guy looked like, right? Let's look at the degrees here: 2, 3, 3, 3, 3, 2, 2. So the minimum degree is 2 here, and that's why these numbers cannot be bigger than 2. Both of them, because this is what it says. The minimum degree in this particular graph was 2. And why is that? Well, let's look at if you have things of degree 2 here. Look, let's talk about this guy first. the edge connectivity. If you have a vertex of degree 2, then I'm claiming the edge connectivity is at most 2. Right, because here's a way of disconnecting this graph by removing two edges. It is very simple. Remove this edge and remove this edge. Because it was, the edges are removed, not the vertex, right? Sorry, this is because I've been sloppy drawing. That's why my eraser doesn't do exactly what I need to do. But remember, so there were these two edges here. They're now gone, right? These two edges removed disconnects the graph. Because the degree is 2, and whatever the degree is, if you take a vertex and you erase all the edges that are adjacent to this vertex, of course, then you disconnect the graph. So that shows you that the edge connectivity can never be more than the degree, because the minimal degree, if you have a vertex of degree 2, just remove the two edges that are adjacent to this vertex and you have disconnected the graph. Because that vertex is now on its own. Okay? So I hope that this part is clear of the inequality. Sorry, I didn't want to box it like that. So this part is clear. The other part, I'm going to leave that for you to read, and perhaps I say something more in the next video. So I haven't finished 10.4. We'll take our time a little bit. There's quite a lot of other things we can say. It's an important concept, graphs. Paths and circuits in graphs, so I want to spend my time on it.